In this unit, we will be looking at test for normality and data transformation. Normality test is a part of EDA, that is exploratory data analysis. It is very essential that you ascertain the state of your data, whether it is normal or not, before you go into your analysis fully. If you look at your fingers, you will see that they are not equal. What about a situation where somebody extends his or her hand to shake your own hand, and you see that that person's fingers are all equal? Will you shake that hand? I think you'll be afraid. Personally, I will be afraid. I will withdraw my own hand. I wouldn't want to shake that hand because that is not normal. That somebody's fingers, should be equal. It's not normal. That is the same way we should look at data. When your data is not normally distributed, you find out that there is something not normal in it. So we try to ensure that our data, before we go into analysis, is normally distributed. So we are going to look at all this, and if we do not meet this condition, we will go ahead to transform our data. So it is expected that at the end of this unit, you should be able to test data for normality and also transform data when it is not normal. So let us use some numerical examples to actually drive this home, because normality issue is a case that should be considered because it's very, very important. If not, it will give you a result that you think is what it should be when it is actually a different thing altogether. Let's say we have a set of data, let's say ages of students, and let's say they are students in 100 level. You know that their ages will be between 18 to 22, like just what I have here. So let's say we try to find the mean, and the mean is what you see, 19.83. And in that, let's say in that same class, when you wanted to make use of this data, you also found out that there is an age in that class that is 35. Somebody's age is 35 in that class. I think you wouldn't want to go ahead to use that data when you observe it. You'll be asking the question, is there anybody who is 35 in 100 level? You would want to go back to the class to verify, to know if actually somebody is 35 in that class, or if you can't reach the class, you would want to look for a way to find out if actually a student in that class is 35 years. And let's say you want to go ahead and look for the mean of that data when there is somebody who is 35 in that class. You see that the mean will be different from what we had earlier. That is from 19.83, it will be 21. Even though somebody may say that if you approximate the first one, you have 20, right? But this is actually not good. I'm going to prove to you now. Let's say we have the mean, yes, 19.5, and we have the mean also for the other data to be 21. Now, let's see what happens, what actually is happening with the addition of that 35, showing that it has actually distorted the whole nature of the data. So this is the standard deviation for the first data, where we have the students between the range of 18 to 22. Now look at a shortcut there. This is standard deviation for the next data. You see 4.4, while normally it is 1.5. You know, our standard deviation shows us the deviation between the average value and each of the values in the data set. Now it shows us that clearly the deviation is not quite much. It is what? 1.5. Now as we added this outlier, because I'll call the 35 an outlier, an outlier is a value that is outside the range of a set of data, either it is high or low. It may be as we have 35, or we may have like 9, somebody who is 9 years in this class. So you see that it has actually inflated the whole thing. It has given us a value that is quite out of the normal, telling us that the deviation between the average value and each of the values in the data set is 4.4, which is quite blown up. So this is the reason why that outlier is a problem. That 35 makes data not to be normal. So before you go ahead to use this data, it will be good that you transform the data to bring everything to normal, or you standardize it. So this is what it looks like when you have outliers in your data. So let us see how we can test our data for normality in SPSS and transform if the data is not normal. So let's go to Excel, where I have some data. If you open your exercise files folder, you will see data named normality test and data transformation. So we have this data. This is money supply. It's real data, Nigeria money supply. I collected the data sometime. So that's what I want to use to test for normality. You know that economic data are always not normal. The first thing to do is to copy your data to SPSS. So highlight the data and copy. Let's go to SPSS. Right click to paste it. So go to the variable view and define it. This is money supply MS. So we'll come to the label area and label it properly. Money supply in bracket M2. The measure is scale. So let's go back to the data view to look at it. Okay, so to test for normality, what you do is you go to analyze, move your cursor to descriptive statistics, go to explore. So it gives you this dialog box. Drag your data into the dependent list area. When you drop it, go to statistics, ensure that the descriptives box is selected. Okay, let's go to plots, click on it. So select this checkbox here, normality plots with tests. I'm going to remove the stem and leaf. I'm not going to do that. So click continue, click OK to run the analysis. Okay, so our result is out. The first table there shows the case processing summary. We have 31 values. There's no missing value. So let's go to the next table, which is the descriptives. If you look at the mean is 26.24 approximately, and our median is 20.70. This, at a first glance, shows us that the data is not normal. Because when data is normal, you find out that the mean and the median will be the same, exactly the same if it's perfect symmetry, or they will be very close to each other. But in this case, it is not the same. The next thing you look at is the skewness and the kurtosis. If you look at the skewness, you see that it is 0.960. So it is not normal because it should be approaching 0. It should be 0 exactly if it's perfect, or it should be 0.0 something, so very close to 0. The same goes with the kurtosis. It should be approaching 0, and that tells us that our data is normal. Okay, that is just for that. Now, the real test, which actually gives us a statistic for our data and also gives us a p-value, tells us exactly whether it is normal or not. We don't have to look at whether mean is closer to median or not, but when we look at the test, it tells us straight away what it should be. Now, we have the Kolmogorov-Smirnov test and the Shapiro-Wilk test outputted. The Kolmogorov-Smirnov test shouldn't be considered at this level because the sample size is not that large. Even though we say in statistics that when data is 30 and above, we say it is large. When it is below 30, we say it is small. But in this case, for Kolmogorov-Smirnov test, the data has to be up to 1,000 or 500 and above to 2,000, 5,000, 10,000. Then the Kolmogorov-Smirnov becomes appropriate test to test for normality of such large data. But the Shapiro-Wilk test takes good care of data that are within this range, that is 30 to 100 and all that. It actually handles it properly, better than the Kolmogorov-Smirnov. So when you have your data and it is not that large, you consider using the Shapiro-Wilk test or some other tests as well. But the SPSS outputs Shapiro-Wilk and also the Kolmogorov-Smirnov. So we are going to use Shapiro-Wilk test. If you look at it, you see that our p-value is 0.009. This tells us that the test is significant. It is less than 0.1, which I usually use for assumptions. I usually consider 0.1, not 0.05. So when I'm doing assumptions, I usually consider 0.1, that is 10%. Okay, so that said, you see that we have violated the assumption of normality in this case. Everything is just pointing down to that same thing, that we have violated it, even from the mean median consideration, from the skewness we looked at, from the kurtosis also, everything, even the test, Shapiro-Wilk test, tells us that the data is not normally distributed. If we have to go for that to also continue to visualize or look at the whole thing, you see that our normal quantile plot, that's the normal QQ plot, shows also that the data is not normally distributed, because if it is normally distributed, all these data points should be able to align on this line, but you see that they are out of the line. So it also tells us visually that the data is not normal. All these things are just corroborating each other. So let's look at the last thing we have, that is our box plot. The box plot has actually shown that there are outliers. Now when you see outliers, these numbers you see are not the outliers. It shows us the row where the outliers are located. Like you see that we have 21, we have 6. The rings are there showing you where they are, but the values are not the values. The rings are the positions where the values are. So let us go to look at these outliers, because it shows us that there's an outlier on the 6th row. So let us jump to our data. To do that, let's click on this star here. It jumps you back to your data. So if you look at row 6, you see that we have 63.3. SPSS tells us that it is an outlier. We have also 64. Let's go back to our output. It says 21 and 6. Okay, let's jump back. 21 is the 64 exactly, 0.9, and also 6 is the 63.3. It says that these are outliers, but I'm actually surprised that it didn't point out 3 and 4. Okay, let's go ahead. Let's go back to our output view. So since SPSS has said that these two are outliers, so let's go on to transform our data, because we have violated the normality assumption. So to transform our data, whether you are in the output view or you are in the data view or even in the variable view, wherever you are, what you do is just to go to the menu bar and click on transform. When you do, click on compute variable, and this dialog box comes up. The first thing you have to do is to enter the target variable, and the target variable is the name of the data you want to output. So the variable name, it shouldn't have space, so let's call it trans ms. Let me put that in the bracket, or let's just use an underscore. So you go to the numerical expression area, click inside and type ln, open a bracket. Ln stands for natural logarithm. Okay, so we want to transform the data using the natural log. Just get the log of all of them. That's one aspect. Actually, there are some other methods of transforming data. You can take the square root of the data, you can do a kind of inverse transformation, and some other kind of transformations. You can also do the standardization, take the z-scores, and all these things are ways of transforming data. But it is usually good, like it is much more common, to find the natural log of your data. That helps us a lot. So now when you type ln and open a bracket, you drag this variable into this place, and when it comes up, you close the bracket. If you have done this, click OK. It has outputted it. Look at it, tells you compute, trans, this and that, execute. So to see your data that you have transformed, just go back to your data view, click on this to jump back to it. So we have our data transformed, but we are not going to go further to do our analysis after we have transformed. What you need to do is go back and test again to know that the transformation really worked or not. So to do that, let's go back to analyze, or we can use this tool to jump back to the previous thing we just did. If I click on it, I'm going to go back to compute variable, but remember we went to explore earlier. So let's click on explore. It takes us back to this place. So drag this one that is inside the dependent list out, and drag the trans ms, which is the one we transformed, into the dependent list. Because everything we selected earlier are still where they are, we don't have to go back selecting again. So what to do is you click OK to run the analysis. So looking at it again, you see that the mean is now 3.045. The median is 3.03. You see, getting closer. Okay, let's look at our skewness. Our skewness is not that bad like it was. It was actually 0.9, even though it was positive, but now it is negative. Something must not be going well. Okay, we'll find out. And our kurtosis is also quite high. Okay, let's look at the test. The Shapiro-Wilk test tells us that our p-value is greater than 0.1, which is good, telling us that the data is normal. It has tried to bring it very close to normal. Okay, so let's continue to look at other outputs. Okay, the normal QQ plot is actually revealing that something may not be going on very well about the data, even though Shapiro-Wilk says it is now normal or very close to normal, and though our kurtosis and skewness are also telling us that something is not going very well. Okay, you see that the data points are out here. Let's look at the box plot. Okay, that is the problem. Look at an outlier has been dictated down here. I think that is the reason why we have those skewness and also the QQ plot telling us that something is not going on well. This is not good at all. The next thing we are going to do, because we have transformed, we're not going to transform the transformed data again. That will not be good. What we will do is to eliminate this outlier, even though some people may not agree with me, because there is so much argument out there with so many research articles about outliers, treatment and all that. Some will not actually agree that you should eliminate. Some will advise you eliminate, and some will try to apply some other methods to take care of it. But in this case, we're going to eliminate because I think it is a good practice also. So let's go back to our data and try to eliminate. Mind you, the outlier is on row 29. So let's go to our data and go to row 29 and see what we can do. Okay, it is that 3 we talked about earlier. Okay, so what I'm going to do is to eliminate it. So click on 29, the row like this. When it highlights all of them, right click and click clear. Okay, so it has cleared it. Let us go back and test again to see what happens. I'm going to use this. I click explore. So we have it. So what to do is just click OK to run the analysis again. I'll click OK. Okay, let's look at the descriptives this time around. So the mean shows us that it is 3.11 and the median is 3.06. If you approximate it, we have the same thing. Okay, this is good. So let's look at our skewness. It has reduced it, getting it closer to 0. This is good. Though it is still negative, our kurtosis has also come down. If you look at our previous result, you see that our kurtosis is high, 7.756. Our skewness is also high, 0.702. That's negative 0.702. Okay, let's go to this one we just did now. You see that it has reduced. As we eliminated that outlier, the data is becoming much more normal than it was. And our Shapiro-Wilk p-value has also increased. What we had before was 0.203. Now we have 0.613. This is good. It has shown that the elimination of that outlier has improved our data. It has brought it closer to normal. You see that the elimination method is not bad, it's good. Okay, I'm an advocate of it, even though there may be better research or articles about that. We'll get to that. Now let's look at our normality test using the QQ plot. You will see that the data is now aligning with the line much more than we had it before. Before we had so many of them out. If you view it, you see, look at about 3 out here, 1 is up there, and these ones are not really on the line. But now that we have eliminated that outlier, look at what has happened. The data has improved and we have only 2 out, and this is not far from the line and they are now on the line. This is good. But let's see our box plot. Okay, the box plot, you see, is pushing the data much more into the middle of this upper whisker and lower whisker, much more into the middle, even though our median is also not perfect in the middle, because when it is in the middle, that shows perfect symmetry. Okay, so we have an outlier which we can find at row 28. I'm still going to go for that to eliminate this outlier. Let's see what happens, if the data will improve further or not. So let's jump back to the data view. It says on row 28, that is this 4. So click on 28. When it highlights everything, you right click it and click clear. So let's go back to explore to also test the data again. I click OK. We have our result. You see, it is much more better. I think it's going to be better this time around. If you look at the mean, it is 3.16, and we have that's okay. Let's say 3.2, and we have also the median to be 3.1. This is better. If you look at the kurtosis, the skewness, you see it is very good this time around, closer to 0. It is 0.021, very close to 0 this time around than we had before. Before we had minus 0.3 something. This time around we have it to be better, and our kurtosis, even though it is now negative and it is 0.467, I think it is closer. Well, we'll find out as we look at some other outputs. Let us look at the Shapiro-Wilk. You see that the p-value has become better than it was. It was 0.6 something, now it is 0.720, so it is good. Better off, making it much more stronger, that our p-value is higher, much more higher than 0.1. This is good. Let's look at our QQ plot, normal QQ plot. You see that it is now much more aligned than it was. We have only one here out and this one is a bit out, but it is on the line much more than it was previously. Let's go ahead. You see that this is much more random now than it was before. Let's look at the box plot. This is perfect. This is better off. There is no more outlier dictated and the data is much more normal and better the way it is. So well, I'm not going to ask you to go through this whole stress, but you should actually, if you are interested in applying statistics. Thank you for being in this unit with me. We'll meet in the next unit.